Okay, today we're looking at this paper that came out recently, very recently actually, in PRL. It's 36 entangled officers of Euler, quantum solution to a classically impossible problem. So basically, Euler had posed a problem, which I will describe later, which didn't have a classical solution, and then these people, a group from India and a group from Poland, they found a quantum mechanical solution to the problem. So the idea is based on.
Go back. So first of all, it's not usual to see a collaboration between India and Poland, but I'm curious if Robert, if you know these people.
No, I haven't met any of them.
Okay, but you know these institutes, though, I presume.
Yes, I know both of these institutes, but I haven't met these people.
Okay, all right, very good. All right, continue, Tathagata.
Yeah, so actually this Karol Zykowski, they were the one who also published that PRX quantum article that I sent about this 5 unsolved problems in quantum information. So I think this group in Poland, they were very much into these problems already. So going into the problem, so it's based on Latin square. So what is a Latin square? Latin square is a d by d array of d integers such that each number appear exactly once in each row and column. So for example, if I'm taking the integers 0, 1, 2, 3, and I can arrange them in this order, and you can see that there are no repetitions in a row or in a column, right? Similarly, you can see it as an array of card suits or card ranks also. So we can generalize this in notion of classical Latin square to quantum Latin square. So what is a quantum Latin square? So it's a d cross d array of elements in Hilbert space H of d dimensions, such that every row or column is an orthonormal basis. So I showed this number 0, 1, 2, 3. You can think of it, you can think of a quantum Latin square made of bases 0, 1, 2, 3. Using, just the quantum version of this, then you'll have a quantum Latin square basically. So every row or every column is an orthonormal basis of a 4-dimensional Hilbert space. And this one at the bottom is a slightly more non-trivial version of quantum Latin square. So you can see that some of the, elements are in superpositions. So so now we move to orthogonal Latin square. So the way I have formatted this slide, there are several definitions, but feel free to stop me if anything is not clear, because it is a bit involved. So what is an orthogonal Latin square? So orthogonal Latin square is 2 Latin squares which are superimposed on each other such that each ordered pair of entries in each cell are they're all distinct. So for example, this is a Latin square made of card ranks, ace, king, queen, and jack. And this is a Latin square made of card suits. And you can superimpose them to get a 4x4 orthogonal Latin square. And this is another Latin square. So this is also called Greco-Latin square because this is, if you see it, look at this 3x3 orthogonal Latin square, it's basically ordered pair of Greek alphabets and Latin alphabets, right? So, you can see that you cannot generate a 2x2 Greco-Latin square because you cannot have 1, 2, 2, 1, 1, 2, 2, 1 and not repeat elements. Example for d equals to 3 is already shown in the previous slide. And examples can be constructed for odd sizes and when the sizes are multiples of 4. And this leaves a very particular number out, which is d equals to 6. So what happens for the case of d equals to 6? So this is where Euler's 36 officers come in. So this is, so it's basically the problem is we have 6 different regiments. Each has 6 officers with 6 different ranks. Can this 36 officers be arranged such that each row and column has one officer of each rank and regiment? So it's basically looking for an orthogonal Latin square for d equals to 6. So you can look at this for card suits, spade, clubs, diamond, and heart. And I have extended, so the people who wrote this paper article, basically they extended this by including 2 more card suits, floret and sun, and each has 6 cards of 6 ranks. And you ask them whether you can construct a 6 by 6 orthogonal Latin square using this. So after Euler posed this problem, I think around 1780, Euler initially had Euler had suggested that it has no solution, but he didn't give any proof. And then in 1900, there was a proof found that there is no classical solution to this 6 by 6 orthogonal Latin square. So, but this article under consideration solves this using entangled officers. So they found a quantum solution to this problem, basically. So to look at this, we need to know what is a quantum orthogonal Latin square. So if you remember, I have already described what is a quantum Latin square, which is like each row and each column is an orthonormal basis. So now we're generalizing to orthogonal quantum Latin square. So which is a d square, a set of d square bipartite states, which can be written as a superposition in Hilbert space of in this product Hilbert space of d dimensions each, and they are orthonormal. And if you write the coefficients as columns, then this block matrix you get, it is block unitary. So it is a bit involved definition, and it's basically saying that I mean, like usual quantum Latin square, we have orthonormality, and the respective there are certain blocks within you can construct certain blocks of this coefficient matrix. Basically, they are unitary, and you can use this Greco-Latin square that I showed, that orthogonal Latin square, to construct a multipartite entangled state. So this is looking at the problem from a different direction. So consider a pure state coming from the product Hilbert space of 4 Hilbert spaces of d dimensions each, and we write psi as a superposition in terms of the basis vectors of in each of the Hilbert spaces, and this coefficients satisfy normalization. And so basically each element in an orthogonal Latin square is an ordered pair of number, right? So what we say is that Tijkl is 1 if Kl is the entry of the ith row and jth column in the orthogonal Latin square, otherwise it is 0. So if we have a Greco-Latin square, we have a corresponding state basically. And the point they make is that such a state is absolutely maximally entangled. So what do we mean by that? So absolutely maximally entangled state is a pure state if it is maximally entangled with respect to all possible bipartitions. So that if you take reductions of k subsystems with k less than equals to n by 2, then you'll get the corresponding density matrix will be proportional to the identity matrix. So this absolutely maximally entangled state is basically denoted as AMND, where n is the number of system and d is the dimension of each system. And for example, for this is AME2D, where Hilbert space, two Hilbert spaces of d dimensions each. And this is an absolutely maximally entangled state for n equals to 3, basically. So this brings us to the, yeah.
Yeah, do you mind going back to the first time you showed the quantum Latin square?
Yeah.
Okay, yeah. So what is their strategy? So they're saying each of these kets is now what each of these kets lives in a Hilbert space that's a tensor product of 4. Is that what you're saying?
So in this case, so this is like, this can be any dimension, not only 4.
Mm-hmm.
So this is, so when we're talking about quantum Latin square, they can be of any dimensions, but if you look at each row or each column, you will get on orthonormal basis of the series.
Yeah. I understand that, and I understand we're trying to make a 6x6, right?
Yeah, but it's not 6x6 of quantum Latin square, but 6x6 of orthogonal quantum Latin square, which is so. Okay, so this was our classical Latin square, and we added a bit of complexity in it by defining orthogonal Latin square.
Yes.
Right. So
every single one is different. So there's, in our case, there'll be 36 completely different things, but they'll each have kind of 2 indices.
Yeah, exactly. Yeah. So we look at this quantum version of this orthogonal Latin square. So it is not quantum Latin square, but orthogonal quantum Latin square, which has an extra added layer of.
Okay. And when you brought up these indices I, J, K, and L, are some of these, like 2 of these, the rank and like the rank of the officer and the regiment they belong to? So which one I is the rank and which one's the regiment? Kind of.
So the way I have introduced this one is, if you look at this, IJ denotes the position of the officer. So I is, for example, for J clubs, I would be 2 and J would be 3.
Okay, great.
And KL denotes this 2 pair. So I can assign numbers.
Okay, so KL is like the rank in the regiment. And then IJ is like the position. Exactly. IJ is the position in the square. Okay.
Yeah, exactly.
Okay.
Yeah.
That helps. Okay, and then so how did you write this? This here.
Yeah, so basically then for each orthogonal Latin square, you have 4 indices, right? So first 2 denotes the position and last 2 denotes the rank and regiment. And you say this coefficient is 1 if for ijth position the corresponding rank and regiment are k'd. Does that make sense?
Yeah. Yeah, I think so. And I think clearly then every state's going to be orthogonal to everything else. But the point is that we're not doing the quantum Latin square. We're doing this orthogonal thing? Is orthogonal square or whatever?
No, so the thing is, if the states you get using this
Oh, it's a summation.
is
Okay.
an orthogonal quantum Latin square. Yeah. So the point I'm trying to make using this is for each orthogonal. So I think I have an. I have a example. I'm coming to it. So
Okay.
the point I'm trying to make is for each orthogonal. So each Greco-Latin square or each orthogonal Latin square, there is you can always construct a quantum or orthogonal quantum Latin square just by using those elements. And the corresponding state that you defined in such a way is going to be absolutely maximally entangled.
But the elements of this square, are they given just by the terms of the summation?
Yeah, so the element of the squares you can, so for the ijth position, the corresponding element will be KL, KL. So I'm coming back to it.
Okay.
I'll give an example so it will be clearer.
All right.
So the point is this state is absolutely maximally entangled. And I described how for 2 systems or 3 systems, you can get what are the absolutely maximally entangled state. And that brings us to the question of how the absolutely maximally entangled states would look when n equals to 4. So in this case, the way I have defined, so the way the states are defined, this is an absolutely maximally entangled state for n equals to 4 because there are 4 Hilbert spaces in D dimension. And it is interesting to note that AME42 doesn't exist. If you remember that that Greco-Latin square of order 2 does not exist. So the corresponding quantum solution also doesn't exist. The absolutely maximally entangled state.
Sorry to interrupt, Tathagata, but about what you just said. So you said that these states constructed from the orthogonal Latin squares are absolutely maximally entangled.
So
sorry, I was not finished. Is it true the other way around? Meaning that any absolutely maximally entangled state can be written as the kind of sum you have above? I mean, maybe it's not in the paper, but
I'm not sure about the answer. I would suspect yes, but I'm not sure about the answer.
Okay.
Yeah. So going forward, I'm giving an example. I think this will make the things a lot more clearer. So this is a Greco-Latin square of order 3, size 3, basically. So for 1 position, let's assign the ket 2 3 because 2 3 is the ordered pair in that position. For 1 2, let's assign this ket 3 1 and so on. So in this case, these states defined as 2 3 3 1 1 2 3 2, this constitute an orthogonal Latin square, orthogonal quantum Latin square. And the state defined by this, where the first 2 are the position of the row and column, and the last 2 are the corresponding ordered pair, like 1 1 2 3, 1 2 3 1, 1 3 1 2. This state constructed in this way is the absolutely maximally entangled state associated with this orthogonal quantum Latin square. And so it's basically 2 separate notions which correspond to one another. One is orthogonal quantum Latin square, which are like an array of quantum states. And another is the absolutely maximally entangled states. So for an array of states, you can get an absolutely maximally entangled state. So this brings to the question of how about AME 4-6, because we know that the quantum orthogonal Greco-Latin square of size 6 does not have any solution. So Euler's 36 officers cannot be arranged classically, but it turns out that this AME absolutely maximally entangled state 4-6 can be found. And that's what we show here. So I think the answer to the question is yes, that if you find an absolutely maximally entangled state it will have to be of size of 4 subsystems, but you can always find a corresponding orthogonal quantum Latin square. And I have a reason why I'm saying this, because so in that paper, they prove an equivalence where they show that in the supplementary material, basically, that construction of an absolutely maximally entangled state 4D is equivalent to construction of an orthogonal quantum Latin square of size D. So, solving one of them is going to simultaneously solve the two of them. So let's look at how they solve for this absolutely maximally entangled state AME 4-6. So we have this Hilbert space, 4 Hilbert space of 6 dimensions, and we have this psi written as a summation, as I had shown before. So they solve the problem of finding this Tijkl such that this state is absolutely maximally entangled.
Sorry, can we go back to like what actually makes something absolutely maximally entangled?
Yeah. Yeah.
Pure state if it's order. Okay, sounds complicated.
Yeah, so the way I understood is if you have n subsystems and you can trace out such that the number of subsystems you have remaining after tracing out is less than equals to n by 2, then the density matrix is going to be proportional to identity. So, I mean, I have been thinking it a bit mathematically, but I mean, each subsystem, each bipartition is maximally entangled.
Okay. So
I don't have the.
If it's 8 qubits, for example, if you trace out like 4 of them,
yeah,
you could say like maximum 4, right? Is that what's required? It says k less than or equal to n over 2.
At least 4. So the reductions will be subsystems with k less than equals to n by 2.
Yeah, so I don't know. It sounds to me like what they're saying is you could trace out, if you trace out 1, 2, 3, or 4 out of 8 qubits, all of these have to result in maximally mixed states. Is that kind of what they're saying?
The way I understand is they're saying you have to trace out 4 or 5 or 6 of the qubits, because you're reducing it to k subsystems with k less than equals to n by 2. So you'll have to trace out more than 4 out of the 8 qubits, 4 or more than 4.
So k is the number you end up with after the partial trace. Is it like that?
Yeah.
Okay. 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 So all kind of smaller than half I guess subsystems are considered max-limiting. Okay.
Yeah.
So they're finding the elements that happen to produce that. Right?
Yeah. So, and they go about it in a different way where, so for this coefficients Tijkl, what they define is a matrix of size d square by d square, where the number of rows are so Ijkl, they rearrange it in a matrix where the first, the row number of the matrix is dependent on the INJ, and the column number is dependent on the indices K and L. So you get a matrix of size d square from this tensor of size 4 into d, basically. So, and this is a permutation matrix, because if you remember that for each ij, there is only one KL that would give the ij KL is 1. That's the way the orthogonal Latin squares are defined, right? So this U ij KL, this matrix of size d square by d square, there will be a permutation matrix. Now, they define this partial transpose and reshuffled matrix. So partial transpose is basically transposing with respect to the last indices J and L, and reshuffled is shuffling this J and K indices. So, and it turns out that because this is a permutation matrix, this partial transpose and this reshuffle matrix, they are also permutation matrices. So now they're looking at this from a different perspective. So they're saying that for a permutation of order d square, it will give you an orthogonal Latin square or Greco-Latin square if the corresponding reshuffled and the partially transposed matrices are also permutation matrices. And now they prove, going further one more step, that if instead of a permutation matrix, if you look at unitary matrices such that the reshuffled and the partial transpose matrices are also unitary, they're calling it 2 unitary, then the corresponding state you get is absolutely maximally entangled state. So for a 2 unitary, you can get the absolutely maximally entangled state by defining psi as ij, psi ij, where psi ij you get by applying this 2 unitary on this ij. Okay. So this corresponding state is absolutely maximally entangled state. So they use this idea. Now the problem of finding Tijkl has been reduced to finding a 2 unitary matrix. And this corresponding psi ij, these elements, they form an orthogonal quantum Latin square. So they solve this problem of, okay, before we go into that, so now they have 3 equivalent statements. Construction of absolutely maximally entangled state 4D is equivalent to construction of orthogonal quantum Latin square of size D, and is equivalent to finding a 2 unitary of size D square. So by solving this one, they solve all this. There is another equivalent statement including perfect answers, which I have not shown here. It's not important for this discussion as of now. So how do they solve it? So they use, I don't know the numerical procedure they have used, but apparently they had a previous result which was also published in PRL, and this was only the Indian group, where they had some way of finding these two unitaries. Okay, I think I need to. Okay.
This is the intermission.
Yes. So basically, they find this two unitary for this d equals to 6 and solve this problem of Euler's 36 entangled officers. So this is the solution they get. So this is showing the non-zero elements of Tijkl, where this row, this indices mentioned along the row, the 6, 3, 1, 1, 5, 6, 4, 2. These all are showing the position of the elements, and the corresponding KL are shown here. This corresponding Tijkl values are shown in terms of A, B, C, and omega, where A is this value, 1 over square root of 5 plus square root 5. B is this, C is 1 over square root 2. And omega is a 20th order root of unity. And apparently this, so this B by A is actually golden ratio. And that's why they call this state golden, absolutely maximally entangled state. And and each row, so if you look at each row of this this diagram, basically, they will give you the corresponding entangled officer for this particular position. So for example, in 1, 1, this is an entangle between 1, 2, and 2, 1, where C is 1 over square root of 2. And they have one more way, they have provided one more way of visualizing this entangled officers. So where they constructed the orthogonal quantum Latin square of size 6. So each of these ranks and suits of these cards, they correspond to a number basically. And the corresponding elements show the for each position, what are the states you'll need to consider in a superposition. So, and the sizes of this gates, for example, if you look at A of spades, A of club, ace of club, this is really bigger compared to this Q of club, which denotes that the coefficient, so this corresponds to the corresponding coefficients in front of these states. So, and you'll see certain patterns they find. For example, they never see color mixing in between this entangled officers basically. And also ace is always with king, 10 is always with 9, queen is always with jack in all this. And yeah, so this is, so instead of, so the classical solution would be each row, each cell would have only one of the items from here, but that doesn't exist. But instead, what they have found is a superposition of these officers of different rank and regimes, such that you have a quantum orthogonal Latin square, and correspondingly, there is an absolutely maximally entangled state of 4 systems, each of dimension 6. Yeah, so this is the result. That's it. Any questions?
Yeah, I have one question. Is the claim here that this is the only 6 by 6?
No, I
Yeah.
don't think so. This is the one they found.
Yeah.
From what I understood. But
yeah,
I'd
be curious to see the procedure for generating these things.
Yeah,
you're saying was that in the previous paper by the Indian group? Yeah.
Yeah. So they use this one. I think this procedure will be interesting to look at. I mean, I am very much curious to how they generated the unitary, but I'm suspecting that because you're generating unitary matrices, I think you can get away with applying unitary transformations to the unitary matrices and then still preserving the 2 unitariness of the matrix. And therefore, you can have like multiple absolutely maximally entangled states, basically. I mean, I don't see why you can't have more than one absolutely maximally entangled state.
Well, this is of course is an analytic solution, right? There's no numeric.
Yeah. I think they use a numerical procedure to solve for this. I'm not exactly sure about the procedure. So let me try to find this corresponding statement. So in their paper, they mention that we use an iterative numerical technique based on union in the space of unitary matrices to find this 2 unitary matrix of order 36. So although the solution is on analytical, they used some numerics to find it.
But then it says below, finding the analytic form was a major challenge.
Yeah. So I think
they probably found it numerically first, just numbers,
yeah,
and then they had an analytic solution.
Yeah, maybe. Yeah.
Right. So that's where this all of this decomposition between the 2 unitaries. That's all analytic methods.
Yeah.
So can you show? Let's look at this solution again, Tathagata. Can you go back to the final solution?
Yeah, I can show it on the paper. This one basically.
I wanted to see your card picture.
Oh.
Seeing it like that, yeah.
Yeah.
So now, if these were classical solutions, you would want to have each row and each column doesn't repeat, isn't that right? So you would have only one for each row and each column, something like that.
Yeah, here also they don't repeat, but it's like they are in superposition.
Okay, yeah, that's something I don't quite understand. Like, it seems like I have clubs in the top row twice.
But the ordered pairs don't repeat.
Yeah, so if I look at like 10 of spades, 10 of clubs, 9 of spades, 9 of clubs, like I see that down at the lower right-hand side, for example, which doesn't repeat. The far right corner. Okay, so that's it's in a different row, different column, so that's fine.
Yeah, I think some of them differ in coefficients. For example, in this case, this one has the largest coefficient, and this one, in this one, this 10 of spades has the largest coefficient. So although this and this looks very similar, but I guess these are different states.
So are they like different and orthogonal states?
I think these are all orthogonal to one another as per the definition of orthogonal quantum Latin square.
But I think it's only orthogonal in the rows and the columns, right? So only if you go down one column or go across one row are they all orthogonal. Isn't that right?
Yeah.
So I took like the 1-1 entry and compared it with like the 3-3 entry. There could be overlap between those two states in principle. Isn't that right? I don't think here there's not, but there could be.
Yeah. So they satisfy. So they have this orthogonality relation for this orthogonal quantum Latin square. Psi ij psi kl would be delta ik delta gel. So I guess k has to be same as I, ll has to be same as j, which means that the way I understand it, two different elements will be always orthogonal.
I see.
For this orthogonal quantum Latin square.
Yeah. Okay. Yeah. So like the classical Latin square, if you go back to that picture, Tathagata, yeah. So there, basically every element has something different, right?
Yeah.
So the might be in common, but then the suit is different, right?
Yeah.
Or the suit may be in common, but then the card number is different.
Yeah, that's right.
Okay. Yeah. So but you're right. Every element is orthogonal to every other element then.
Yeah.
Okay. Interesting. So even though some of them look the same, like that example we showed, it must be the coefficients are arranged such that they have zero overlap. So they must be like orthogonal in the subspace.
Yeah, I guess
so. Okay, interesting. Yeah, and I put this paper that Tathagata pointed out in the chat that the same authors wrote about these 5 open problems in quantum information theory.
Yeah.
So some of them have to do with
this one.
Yeah, so some of them have to do with like these POVM symmetrically informationally complete, I think, POVMs. Yeah.
Problem 1. Yeah.
Yeah, problem 1. And then others, yeah. So I think I was talking with Chris Fuchs about this problem too. That some solutions don't exist in certain dimensions, or they don't know if they exist, I guess.
I see.
And then the other ones actually they talk about some problems in metrology.
Quantum problem 3.
Yeah, and I think they cite this paper we had written with Jing and Shengxi and collaborators at some point. I think if you look at reference 108 is I think they cite this our paper.
Oh yeah.
And that's generalizing this multi-parameter quantum metrology to mixed state case. Okay. All right.
Okay.
Any other questions about this paper? Or
thank you to Tathagata. That was really good. Seems like a very complicated subject, and you did a good job. I'm, I guess, still just kind of struggling to see like how this solution like is in keeping with the spirit of the original classical problem, where like the goal was to represent each rank and regiment once in each row and column. Like, how is this quantum solution like I don't know, how is it doing a similar thing?
well, the way I understand it is that you generalize this notion of rank and regiment to be quantum superpositions of rank and regiment, such that in these quantum ranks and regiments, you can have indifferent rays that correspond to orthogonal entangled states, and the idea is that those don't repeat and that they're orthogonal with each other, but nevertheless that they're all represented in this square. So, do I get that point right, Tathagata?
Yeah, I think so.
So, I mean, it seems like it wouldn't be difficult to arrange like 36 orthogonal quantum states in a square. Like there are like a million different ways you could do this. But is the point that like you're utilizing these, in this case, I guess, tensor product of two 6-dimensional spaces in order to create these?
I think there are extra constraints, right? It's not just they are arranging.
Yeah.
You need to take into account also that they need to be latent square, quantum latent square. So that's like an extra constraint that you have to satisfy. So,
well, I understand these states are like of a certain form, right? They're like, superpositions of, yeah, like they're this form A1. With n equals 6, I guess, yeah, or maybe it's
something like that.
Two summations there, maybe. Maybe there should be, yeah, but yeah. I mean, what was the other? What are the other constraints? I mean,
so it's like the if you write the coefficients in columns, the columns should be block unitary, which is like parts of the column would be unitary, like these two constraints basically. So I think 6 cross 6, I think if you write out this 6 cross 6, it won't be as easy because obviously the classical solution does not exist.
Mm-hmm.
So yeah, well, then basically relaxing some of the constraints to get a superposition. If finding if a superposition would work instead of an ordered pair of rank and regiments themselves.
Okay, I mean, I guess what I understood is that when you choose different n and d, for some choice of n and d, right, there is a classical solution, and using that construction to like, using that as inspiration for constructing a quantum state, you end up with a absolutely maximally entangled state.
Yeah, but n has to be 4 when we're talking about Latin squares, orthogonal Latin squares, because there is row and column ij, and there is also an ordered pair k. So n will be always 4. The d would depend on the size of the square we are using.
N equals 4. Yes. Yeah, n is always 4.
That just sort of spurred an idea for me. Could you go fast, or could you go higher than 4 there? Like, could you do like 3, ordered triplets or something? Is there anything?
I don't see why not, but
like Greco-Latin square, yeah.
Super Greco-Latin square, something like that. But
are we talking about tensors instead of?
I mean, I think what it's basically is like you could have try to arrange things on a cube, and instead of rank and regimen, you have like rank, regimen, and like, I don't know, height or something, some third variable.
Ah, okay.
And then I guess then n equals 6, like 3 times 2.
Yeah.
Okay, no, fascinating subject and really nice work by this Polish Indian team. Really intriguing.
Yeah.
All right. I'm gonna stop recording now. So thank you again to Tathagata. I've decided that